Good morning. I hope you guys are doing well today. Kind of a small class, um, so hopefully a few more people find their way in here. I just have a few announcements before we get started today. Let's see, I got Rachel and Rebecca in here today. I need senior pictures for the slideshow from you guys still, so if you can try to get me a current picture with future plans by May 1st. And then, Rebecca, if your mom wants to send in a baby picture with a congratulatory note, she can do that as well. Even if you don't plan on attending graduation, I'd still love to include you in the slideshow because you worked obviously really hard to get to this point, and we'd love to recognize that. So if you guys have pictures, make sure you send them my way before that May 1st. I also want to congratulate Rachel in here. Isaias isn't here yet, but maybe he'll make his way in this morning. Rachel is our valedictorian for the class of 2018, and Isaias is going to be our salutatorian. So congratulations to them for all their hard work, and yeah, it's really exciting, isn't it? So congratulations to Rachel and Isaiah. So hopefully finds his way in here shortly. All that hard work finally paid off, right? You can see the light at the end of the tunnel. Um, all right, now that's all I really have as far as announcements go, other than make sure everyone keeps moving forward and staying on pace with that calendar. We are nearing the end of the school year, so we got like a month left until that final deadline, which is May 20th. And May 20th is that last day to turn any work in for the semester that's not the final exam. For any juniors in here who took the ACTs, I know there's a bunch of you. I sent out an email, I want to say last week, for those who have not filled out the form yet and who have taken the ACTs for your final exam exemption pass. So you will be contacted, I would say, probably the week of the deadline or maybe the week before, even by the teacher of your first choice to let you know if you qualified for the final exam exemption pass. And if you didn't, the second person or the second class in line will then be notified to see if you qualify for that, and then so forth. So any questions with like final exam passes for the juniors who took the ACTs or the final deadline? Any questions with that at all? Okay, if not, how about questions from 9.02? So that was your binomial theorem. There were 5 questions on the homework. Most of it seemed to go pretty well, but anything you'd like to go over or review from that lesson to start us off today? Just one thing, I see Rebecca typing, so I'll wait for her, obviously. But one thing to take away from that 9.02, don't forget to use your calculator to help you with the expansion of your binomial theorem. So your binomial theorem is all tied around combinations, right? So you can use that combination tool on your calculator to help you find the expansions. So, for example, I think one of the questions was like what number, I think the first question in the homework was something like what number is not in the expansion of something to the 10th power. you can go ahead and use your calculator, don't forget, to find out what those coefficients are going to be of your expansion. Yeah, so if I take a look at question 1, it says, which of the following numbers does not appear in row 10 of Pascal's triangle? You can use your calculator there. So what we would do is you're looking for row 10. You would then, in your calculator, choose that NCR capability. And then it gets a little cumbersome, but we want the 10 choices. So we got to start at 0, because remember Pascal's triangle actually has a row 0, even though we don't look at that too much because it's just a 1 to kind of start us off. But then we would include all of these numbers with commas in there all the way up to 10. And when you do that and you hit enter, it will give you all the coefficients for the row, right? So that expansion, we use Pascal's triangle for the binomial expansion as well. So most of the questions, I would say, can be solved by using this combination tool on the calculator. Okay, so work some more with that. It takes a while to get used to the binomial theorem and Pascal's triangle, but when we can see the relation between the binomial theorem and Pascal's triangle with those coefficients, it kind of meshes nicely together. And if we realize how we can find the coefficients in Pascal's triangle by using our combination tool, it all kind of fits nicely together. Today, we're going to be focusing on sequences. So we have two types of sequences that we've seen in the past that we're basically going to revisit today. That's our arithmetic sequences and geometric sequences. So we will be looking at those two topics today. All right, so the first thing on our list when we look at sequences is, first of all, what is a sequence? So a sequence is just a list of numbers. The list of numbers can be finite, so meaning it has a start and an end, like example 1 here. So we have a starting value and we have an ending value, right? Notice there's no ... after it. So we can have finite sequences, or we can have infinite sequences, and that's where your ... comes in, right? These ... mean that the pattern just continues forever out in that direction. The other thing I want you to notice with those infinite sequences is that they will generalize the pattern that's happening by using the letter K, right? So they call this the kth term. Sometimes they use n. I like the nth term better. When we get to our particular sequences, they use n instead of k. So I like the nth term better. Like, I'm kind of used to saying that versus the kth term. But it means the exact same thing. It's just a generalization of what's happening in that pattern. So you'll notice that the pattern in number 2 is just raising it to the kth power. So if k is 1, that helps you find the first term. So 2 to the first power is 2. If k was 3, that's referring to the third term in the sequence. So 2 to the third power is 8. So that pattern will, or that generalization will help you find each term in the sequence. All right, let's actually look at some examples now. So the first example here just says find the first 6 terms and then the 100th term of the sequence given where a sub k equals k squared minus 1. All right, now this is just basic substitution. So when we're finding a certain term given an equation here for a sub k, we're just going to substitute that k value into our equation and simplify. So the first term would be when k equals 1. Okay, so what do we get when k equals 1? Well, let's see. We have 1 squared minus 1. And what does that result in when we simplify? Yeah, a 0, because 1 squared is 1, 1 minus 1 is 0. So that means the first term of the sequence is 0. Okay, how about the second term of the sequence? So that means that k will equal 2, and when I substitute 2 into our equation, what do we get for an output? Yeah, 4 minus 1 is 3. So the second term of the sequence is 3. And we're going to keep going, so I'll let you guys kind of fill in the board here for the first 6 terms. I'll let you write the number after my arrow here at the end. So go ahead and simplify those for me and put those values in after my arrow. And we'll find the first 6 terms here pretty quickly. Good. And then it also wanted us to find the 100th term. Well, there's nothing extra spectacular that has to happen to find that. We're just going to substitute 100 in for k, although the number is going to be significantly larger than what we've had for the first 6 terms. But the pattern just keeps continuing. Nothing special has to happen once we reach that level. So what is going to be our 100th term of the sequence then? Yeah, so 10,000 minus 1 is 9,999. Lots of 9s. 9999. Good. Any questions with finding the terms when you're given an actual equation for a sub k? So nothing too, I don't think, too spectacular or out of the ordinary there for that type of pattern. All right, now this is what we kind of call an explicit equation or formula because they tell you exactly what to do here, or they give you that equation with k in there. We have another type of formula that's a little bit different. It's called the recursive formula. So the recursive formula is more describing the pattern that's happening in the sequence and not necessarily giving you the exact term, right? So if the explicit formula up here I think is a little bit easier to use because there's not much to it. You just substitute the term in and simplify to get your result. The recursive formula you have to work a little bit harder for because what the recursive formula allows you to do is you need the number before it, and then whatever the pattern is, you're going to apply that to the previous number, right? So if I could pick up a pattern here, I would have to apply the previous number in order to find the next term. So it's a little bit more confusing with the recursive formula. So here's an example of what I'm talking about. It says find the first 6 terms again and the 100th term for the sequence defined recursively by the conditions b sub 1 equals 3 and b sub n equals b sub n minus 1 plus 2 for all n greater than 1. All right, so what these notations actually mean is b sub 1, where n is 1, that's your first term, right? So the first term in this sequence is 3. So basically that's what we use when n equals 1. And maybe I should change that to an n equals 1, just so we're kind of using the same notation consistently here. So the first term of the sequence is 3. It tells us that. To find the next number in the sequence, we have to use this pattern down here. So to find the next number, which would be b sub 2, or when n equals 2, we are going to take the term before it, so that means we're going to use 3, and add 2 to that value. So to find the second term, we're going to use 3 plus 2. So 3 plus 2 is a 5. Okay. To find the next term in the sequence, we use the number before it, which was 5, and we add 2. So the third term in this sequence is 7. What's going to be the fourth term, fifth term, and sixth term? So let's go ahead and fill that in real quick. And we got to go in order to find these now. So you have to use the term before it in order to get the next number. Yeah, so 9 would be the fourth term. 11 is the fifth term. 13 is the sixth term. Any idea what we can do to find the 100th term without listing all 100 numbers? I would try to see if I can notice a pattern between n and its output. So you could list technically all 100 numbers, but that's crazy. That would take a lot of time to do. So I noticed the pattern that I can take n and multiply by 2 and add 1, because 2 times 2 is 4, 4 plus 1 is 5. 3 times 2 is 6, 6 plus 1 is 7. 4 times 2 is 8, 8 plus 1 is 9. So I can see this pattern actually happening here of taking that term, multiplying it by 2, and adding 1. Right? So what we do when we notice that pattern is we kind of establish an explicit formula that will help us find that 100th term a little bit easier. So if I can notice that, I can now find my 100th term by just substituting 100 in for n. So what do we get for that 100th term in this sequence? A 201. Yep. So the recursive formula is not as nice. It's a little bit more challenging to work with. But as long as we can understand the notation here, hopefully we'll be able to make it through. Most of the time, the good news is most of the time we're working with explicit formulas versus recursive formulas. So that is the good news, is that we don't work with these recursive formulas too often. We do spend most of our time with explicit formulas. But it's important to know what this notation actually means. So the recursive formula is generalizing a pattern that you're noticing. Okay, any questions with those first two examples before we dive a little bit deeper, I guess, with these concepts? Okay, the next thing we're going to talk about is the limit of a sequence. So we've heard that term limit before. We actually looked at that in first semester when we kind of just started pre-calculus out. What does limit mean? What do you guys remember when we hear that term limit? Uh-oh, we hear crickets. Limit, remember, is kind of like an asymptote almost. It's what your sequence gets close to, but maybe never really touches, right? So we're really going to explore this concept of limits pretty closely as we move through the last unit of pre-calc as well, because that's starting to get into our calculus topics. But we can look at it here with our sequences as well. So when we see our sequence, which is our list of numbers, is that list of numbers getting closer and closer and closer to a certain value, or is it just expanding indefinitely? So is it just growing without bound type of thing? So that's what we're going to be interested in with this next topic. Now, if your sequence gets closer and closer and closer to a certain value, we say that that sequence converges. Okay, and what it converges to is the limit. So we have some examples down below where we'll explore that idea a little bit further here. Now, if the sequence just kind of grows exponentially and it doesn't really get close to a certain value, we say that that sequence diverges. So diverges means it keeps growing without bound. It kind of goes to infinity, so to speak. Okay, so that's the difference between converging and diverging. So let's go ahead and take a look at the examples below here. Determine whether the sequence converges or diverges. If it converges, give the limit. So what is it getting close to? So we're starting off with the pattern 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, so forth, all the way to 1 over n. So what we have to decide is this getting closer and closer to a certain number as it keeps growing or going up, 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 and up? So what do we think? When I turn these into decimals, it's a little bit easier to identify as well. So are we getting closer and closer to a certain value? And if the answer is yes, then what is that value? So I converted the first 11 terms there, but it will keep going. Are the numbers getting closer and closer and closer to a certain value in this pattern? What do you guys think? Yes or no? Or is it increasing without bound? So are they just getting so large that it just keeps growing exponentially? They're not getting bigger. They're not growing exponentially, right? So that means it's converging. It's going closer to a certain value. So we got to figure out what that number is. What is it getting closer to? When you take a look at those decimal values, what are they approaching? So what integer value are they approaching, but maybe never touching? So as you keep getting larger and larger and larger for that n value, what is the outcome getting closer to? 0. Yeah, so we would say this converges to 0, right? Good. And technically, the way we can do this, and we'll need this in the future as well, but if I were to technically say n is infinity, right, because n can keep going on forever, if I ever get 1 over infinity, we can technically say that will equal 0. So 1 over infinity is the same thing as saying 0. It's not quite 0, but you can round it to 0 because it's getting close enough there. So that's what we would do here to figure out what it converges to. We would put an infinity in for n and see what that simplifies to. So 1 over infinity would result in that 0. Let's go ahead and take a look at part B. So we get 2, 1.5, 4/3, 5/4, and the pattern continues. So the pattern that I'm noticing is maybe we'll have n in the denominator and n plus 1 in the numerator, right? So that's kind of the pattern that we see here to get each term in the sequence. Now, if I change those to decimals, it helps us to visualize what's going on a little bit better here. And I can keep going, like 6/5, 6/5 is a 1.2. And I'll go on for a few more here. But what do you notice? Do you think this sequence is converging, or do you think this sequence is diverging? So remember, if it diverges, it's got to be growing without bound exponentially. Definitely looks like it's converging because it's getting smaller. All right, so if it converges, what is it converging to? So what are the numbers getting closer and closer and closer to, but maybe never reaching? It looks like they're getting closer and closer to 1. So we would say this converges to 1. So the limit of the sequence is 1. The values are getting closer and closer and closer to that, but it never reaches it. How we can show that algebraically is I can simplify this pattern right here that I noticed with n. So I can rewrite that as n over n plus 1 over n. N over n simplifies to 1. And if I put infinity in for n now, I know that will equal a 1 plus 0, which is a 1. So algebraically, I can figure out what that's going to converge to by kind of splitting up that pattern I noticed with the n there. Okay, but you also can figure it out just looking at your list of values as well. Okay, what about part C? Is part C converging or diverging? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. It's getting bigger, right? Definitely getting bigger. Is there a limit to it though? So is there a kind of a bounded region, or is it just kind of keep going forever and ever and ever? It keeps going, right? There's no end to it. It just keeps adding 2 each time. So if there's no cap to it, then we say it diverges. So this is an example that diverges. You cannot find the limit of something that diverges. All right? Part D. What do we notice with part D? Is it converging or diverging? It goes -1, +1, -1, +1, -1, +1. And it keeps rotating back and forth between +1 and -1. Is that an example of converging or diverging? What do you think? Because it doesn't really fit either of the patterns that we've heard so far. It actually is an example of diverging. Yep, if you can't find an exact value of what it's approaching, it will be diverging. Yep, it's going to continue forever in that pattern between -1 and +1. And because it's never really approaching a certain value, it's just oscillating between the two, we say it diverges. Good. Okay, any questions with those couple of examples? This will not be the last time that we look at limits or converging and diverging either. So this is going to be a topic that we take with us into Unit 10. Okay, algebraically, let's see if we can find if the sequence will converge or diverge. So we have to do this all algebraically here. All right, what about part A? What do you think? Well, first of all, let's relate converging to something we already know. So converging means we get closer and closer and closer to a certain value, but never reach it. So that should remind us of what? If we get closer and closer and closer to a certain value, but never cross over it, what does that remind you of that you already know how to find and do? It should remind you of asymptotes. Very good. So what type of asymptote are we most interested in for our series? Are we interested in vertical asymptotes or are we interested in horizontal asymptotes? So which of the two asymptotes are we actually paying attention to when we're looking at sequences? You got a 50-50 shot here, vertical or horizontal. Ooh, good guess. It is horizontal. Yeah, so if I go back to the previous slide here, and if I were to actually plot the points to maybe A or B, we would get something that looks like this, right? Where it gets down, 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 and really, really close to that certain number. Well, we're interested in that horizontal asymptote. So what is this value down here that they're getting close to, but never crossing over? So we are interested in horizontal asymptotes when it comes to these sequences. So if we can remember our horizontal asymptote rules, we should be able to find what the value will converge to quite quickly because it will be that horizontal asymptote. It gets close to that horizontal asymptote, but it's not going to cross over it. So I'm going to bring you back to the rules we have for horizontal asymptotes. All right, remember n is talking about the degree of the numerator. So when I give you these rules, n is referring to the degree of your numerator. M is referring to the degree of the denominator. Okay, so if n equals m, right, there is a horizontal asymptote. Anybody remember how to find the horizontal asymptote when the degrees are equal in the numerator and denominator? To find that horizontal asymptote, we pull the leading coefficients from each part of the fraction. Okay. If n is greater than m, and I've got to just take a look here, n is greater than m, there is no horizontal asymptote. If there's no horizontal asymptote, do you think that is a sequence that will converge or diverge? So if n is greater than m, that's going to be your example of a divergent sequence, right? There's no horizontal asymptote that's going to cap it, so that's going to be a sequence that diverges. If n is less than m, we say there is a horizontal asymptote at y equaling 0. So basically, if that degree of the numerator is less than the degree of the denominator, it's going to converge to 0. That's what that's going to say. All right, let's take a look at the examples then and see if we can apply these rules to see if, first of all, is the sequence going to converge or is it going to diverge? And if it does converge, what is it going to converge to? Find the limit. So part A, what are we looking at with part A? Are we looking at n equaling m, n greater than m, or n less than m? So which one of these do we have happening in part A? Not greater than. If I look at the degree of the n value in this case, I have 1 and 1. So if the degrees are 1 and 1, yeah, I know. I think you're looking at the coefficients at first. So if the degrees are 1 and 1, that means they're equal. So if they're equal, there is a horizontal asymptote. So if there is a horizontal asymptote, we say that converges. So in this first example, it will converge. Now, what will it converge to? Find the limit. Well, what is the asymptote, first of all? Because if you can find the asymptote, that will be your limit. So to find the asymptote, we take the coefficients of each part. So the coefficient of the numerator is 3, and the leading coefficient of the denominator is 1. So 3 over 1 is going to result in a horizontal asymptote of 3. So that is going to be what it converges to. It's going to converge to 3 because it's going to get closer and closer and closer to that horizontal asymptote, but it's not going to cross over it. Okay. What's happening in part B? So which one of these scenarios do we have going on in part B? Yep, n is less than m because 2 is less than 3. So if we look at the rule, that means there's a horizontal asymptote at y equaling 0. So will this sequence converge or diverge, knowing that fact? So will that sequence in part B converge or diverge? It's going to converge. And what's going to be the limit of that? In other words, what is the asymptote? 0. Yep, it converges to 0 because that's what the limit is, or that horizontal asymptote. Good. What about part C? Which scenario do we have happening in part C? N is greater than m. If n is greater than m, the rules say there's no horizontal asymptote. So will this sequence converge or diverge? It's going to diverge, yeah. And if it diverges, there's no limit. Awesome. Questions with how we looked at those kind of equations here, or expressions I should say, and related that to our horizontal asymptote rules to figure out if it will converge or diverge. I'll write that. Yeah, n equaling m. So that first one is when they were equal. So I'll put that in there. There we go. Awesome. Any other questions? Okay, there's still a little bit more that I want to throw at you before we wrap up today, and that's dealing with the two special type of sequences. So there are two sequences that we're going to look at, arithmetic and geometric. We've explored both of these in the past, not necessarily in pre-calculus, but probably back in Algebra 1 and Algebra 2 is when we've seen these sequences before. Trying to think, definitely in Algebra 2, because I think I just got done covering that unit in that class this week. So I'm going to give you a little bit more information besides what the test or what the booklet does, not the booklet, your textbook, there we go, with these sequences. So what the textbook gives you is the recursive formula. So the recursive formula is basically that generic pattern, right? And with an arithmetic sequence, you are either adding or subtracting the same number each time to get to the next number in the sequence. Okay, so that's your general rule for an arithmetic sequence. You're adding or subtracting the same value every single time to get to the next term. And that's what they show here with that recursive formula, right? That plus d is the number that you're adding or subtracting to the previous term to get to the next value. The explicit formula they don't give you. So I want to make sure everybody writes this down, because this is the one you're probably going to need to identify certain terms in the sequence. So the explicit formula, just to jog your memory here, is a sub n equals a sub 1. And a sub 1, remember, is the first term of the sequence. N is the number of terms you're looking for, or that certain term in the sequence you're searching for. And D is the difference. What are you adding or subtracting to get to the next term in the pattern? So this is the formula that we want to use to find a certain term in our sequence. Okay. I'm going to go ahead and I'm only going to do one of the examples from down below because I'm running short on time. It says, for each of these following arithmetic sequences, find the common difference, the 10th term, a recursive formula, and an explicit formula. All right, so let's just do number 1 real quick here. First of all, we should be able to identify the pattern there to find the common difference. What are we adding or subtracting each time to get to the next term in this first sequence? And I think it's easiest to identify it when you're looking at maybe two positive terms back to back. Yeah, you're adding 4, right? So if you're adding 4, that means your difference is a positive 4. Good. Now, you can also subtract 2 consecutive terms to figure that out, right? You can do 6 minus 2, 10 minus 6, negative 2 minus negative 6, and you'll get 4 every single time. I'm going to kind of go out of order because the next thing we're going to do is we're going to write that recursive formula. So the recursive formula is your generic pattern. So to find any term in the sequence, you're going to take the term before it and you're going to add 4. Okay. So I know that was a little bit weird, but the notation there is saying to find a sub n, any term, you would take the term before it and add 4. So that's your recursive formula. The next thing we're going to do is find the explicit formula. All right, to find the explicit formula, we're using this right up here. So a sub n equals a sub 1. What is the first term of the sequence in number 1? So what is a sub 1 in number 1? A negative 6. Yep. Now we don't know what term we're looking for, so we'll just leave that as an n. But we know D is a 4. If I wanted to simplify that, I would get negative 6 plus 4n minus 4. So negative 6 minus 4 is a negative 10. So I can technically simplify that explicit formula to condense it down to just a 4n minus 10 there. Okay. Once I have that formula, though, I can use it to find any term I want in the sequence. So when I ask for the 10th term, I can use that explicit formula and substitute 10 in for n. And we can find it pretty quickly then. What is going to be the 10th term of this sequence? A 30. You got it. So that explicit formula I think is really helpful with being able to identify any certain term in the sequence. So we'll definitely want to add that explicit formula to your notes because I don't think I found it in the textbook anywhere, but it'll be extremely useful when you're working through some of the practice problems in today's lesson. Okay. The other thing I want to go through before I let you go here today is the geometric sequence. So arithmetic, you are adding or subtracting to get to the next term. With the geometric sequence, you are multiplying. And you're either multiplying by an integer value or you're multiplying by a fraction. Okay, so technically multiplying, dividing fits that bill. We do have, notice that the recursive formula there, you take the term before it and you're multiplying by the common ratio. The common ratio is that number that you're multiplying by each time, and we denote that with an R. The explicit formula, which this is what you're going to want to add. So the explicit formula for a geometric series is, or sequence, is a sub n equals a sub 1 times r to the n minus 1 power. So again, they left this out of the textbook, but I think it's extremely useful because we can use that explicit formula to find a certain term in our sequence. Okay. Now, while you write that down, I'm going to just fly through an example here from down below. I'm going to do question 1 again. The first thing I have to do is find the common ratio. So what are we multiplying by each time to get to the next number in the sequence? We're multiplying by a 2. Good. The next thing I'm going to do is find the recursive formula. So recursive formula says I can find any term in the sequence, a sub n, by taking the term before it and multiplying by 2. That's your recursive formula. The explicit formula says I can find any term in the sequence by taking the a sub 1, or the first term. Well, what's the first term of the sequence that they give us in example 1? That's a 3. We can take it r, which we know is 2, to the n minus 1 power. So there's that explicit formula using the equation I put up above. To find the 10th term, I will let n equals 10, and I'm going to substitute that into the explicit formula. Now you need to be careful with these geometric sequences because you need to make sure you're doing your order of operations correctly. You must be doing the exponents before you multiply. So as you type this into the calculator, you need to go 2 to the 9th power equals and then times 3. Or you need to type it in just how I have it on the board there if you're going to use your graphing calculator. So you need to include the parentheses around that 2 in order to get the correct response. So the 10th term in this sequence is a 1536. Okay. All right, we're going to stop there. I didn't get through everything. There's probably one more example that you would benefit from. So we'll start off with that example in Thursday's class before I talk about 9.04. If you want to go ahead and open up the lesson homework for 9.03 and try that, you can. But if you want to wait on submitting it until after Thursday's class, I'm okay with that because we'll look at one more example I think that's a little bit tricky and might help with the homework assignment. But if you want to take a look at the homework assignment ahead of time and give it a go, I would encourage you to do so. All right, any questions with what we looked at so far from lesson 3? So it's basically almost done. There's just maybe one more example I think we could benefit from. And we'll look at that at the start of Thursday's class. Okay, if there's no other questions, I'll let you guys go. Have a great rest of your Tuesday, and I'll see you all Thursday morning again. Bye, everyone.